Hello and welcome to Doc Clay's chemistry lessons. Today we're going to be looking at the AQA A-level chemistry course, and this is a year 2 on lattice enthalpy and the Born Haber cycles. So by the end of this lesson you should be able to do the following. We should be able to define the terms enthalpy of formation, ionisation enthalpy of atomization, bond enthalpy, electron affinity, lattice enthalpy, enthalpy of hydration. We should be able to construct Born Haber cycles and calculate the lattice enthalpies and other enthalpy changes. And we should be able to compare theoretical and experimental lattice enthalpies as evidence for ionic or covalent character. Now, as we're going through, do have a look at the card in the top left-hand corner. If you just click on the eye, there are links to other videos and also a poll to have a look at. So before we move on, we'll just remind ourselves of a couple of the basics that we should have met at the end of our Year 12 course. The first one then is delta H, which we describe as the enthalpy change for a given reaction. And this is simply the heat energy transferred in a reaction under constant pressure. It has units that we tend to use or constantly use are kilojoules per mole. Now, enthalpy changes are usually given at standard conditions, and we identify the standard conditions with a theta sign to the top right hand side of the delta H. And standard conditions we mean by undertaking the experiment at 298 degrees Kelvin, which is 25 degrees Celsius, and 100 kilopascals. All of the data we see in this lecture will be at standard conditions unless we state otherwise. The final thing to remember from our Year 12 course is that exothermic reactions give out energy to the surroundings, and these have a negative value for their enthalpy change. And endothermic reactions, well, they take in energy from the surroundings, and these have a positive value for their enthalpy change. Everything else we should revisit from anything that we need from our Year 12 course. Okay, we're now going to go and have a look at what we mean by this term lattice enthalpy. So the lattice enthalpy refers to ionic substances where we're looking at ions which are held together in a lattice. The simplest and most often talked about lattice or ionic lattices is that of sodium chloride, and we've got an example here where we've got our sodium ions surrounded by chloride ions in a cubic lattice. Now, in order to separate the chloride ions from the sodium ions, we have to break the ionic interactions between those ions, and overall we have to overcome the lattice dissociation enthalpy. And we'll have a definition on the next slide, but the lattice dissociation enthalpy is the energy required when 1 mole of a solid ionic compound is completely dissociated into its gaseous ions. So on this side we have the solid, and on the right hand side you'll notice we now have gaseous ions. The lattice formation enthalpy then is equal to and opposite of the lattice dissociation energy. So these are equal and opposite to each other. And the lattice formation energy we can describe as the enthalpy change when 1 mole of a solid ionic compound is formed from its gaseous ions. So on this side we have the gaseous ions, and it's the energy to go through and form the solid ionic product here on the right hand side. The lattice formation energy, we're looking at bond forming, so this is always a exothermic process and has a negative value, and the lattice dissociation energy or enthalpy is bond breaking and therefore is always an endothermic process and will have a positive enthalpy change for the reaction. So I've just updated the picture here with the two values here for plus 787 kilojoules per mole and minus 787 kilojoules per mole for those two lattice enthalpies. Before we have a look at how we determine the lattice enthalpy of dissociation and formation, we'll just have a look at what determines its strength. The magnitude of the lattice enthalpy is a measure of the strength then of that ionic bond in the lattice. In other words, it will determine things like its melting point and so on and so forth. And the stronger the attraction, the greater the lattice enthalpy, and you will get stronger attractions when we have smaller ions and higher charged ions. So we can have a look here at some data. In this example, as we go down the table, we notice that the value of the lattice formation enthalpy decreases, and that is because we're seeing an increase in the size of the positive metal ion. So as we go from lithium down to rubidium, the size of the ion increases, and therefore the attraction is less, and finally the lattice enthalpy is also reduced. If we were then to compare the lattice enthalpies for sodium bromide versus magnesium bromide, we would find that magnesium bromide would have a greater lattice enthalpy because the magnesium ion has a greater charge than the sodium ion, and therefore would have a greater lattice enthalpy. Okay, we're now going to have a look at how we measure lattice enthalpies. The first thing to note then about the lattice enthalpy is that these have to be determined from data. Okay, and that's because we can't directly measure the lattice enthalpy of formation or dissociation. It's just impossible to measure that experimentally. And therefore we have to use a measure a bit like Hess's law. And if you remember, Hess's law stated that the enthalpy change of a reaction is independent of the route taken. And what this means is we are able to calculate an unknown lattice energy of formation or an unknown lattice energy of dissociation by looking at the corresponding enthalpies of formation into the solid ionic state, and how we would then turn these elements into gases by enthalpies of atomization, how we would turn the gaseous atoms into ions here, and also how we would turn any of the non-metals into gaseous ions by electron affinities. And then if we were to follow the route around, going in the opposite direction, we could use this to determine, a bit like we did with Hess's law, the unknown lattice enthalpy of formation or dissociation using all of these key elements. So before we go on and look at how we actually do this calculation, we're just going to go and look at all of the potential enthalpy changes and definitions that we need to know. So we need to know about what the enthalpy of formation, and then turning the elements in their standard states into gaseous atoms in this step here, and then how we turn those gaseous atoms into ions either by ionization energy or by electron affinities. So that's what we're going to look at next, is definitions. So as we saw on the previous slide, we've got several enthalpy definitions that we need to know about. The first two we've already talked about. The enthalpy of lattice formation. Remember, this is always negative in value, and that is the enthalpy change when 1 mole of a solid ionic compound is formed from its gaseous ions. An example is sodium plus ions gaseous plus Cl minus gaseous goes to NaCl solid. It's important in each of these steps when we're describing it that we give the state symbols for any of these reactions. Our lattice dissociation energy then, so this is dissociation and this is going to be a positive enthalpy, as we said, and that's the enthalpy change when 1 mole of a solid ionic compound is completely dissociated into its gaseous ions. Again, we have NaCl solid, and going forward to make Na plus gas plus Cl minus gas. So the first step, as we'll see when we start looking at our Born Haber cycles, is we look at the enthalpy of formation, and this is the enthalpy change when 1 mole of a compound is formed from its elements in their standard states. So an example would be the formation of calcium chloride here, and that's coming from calcium solid and Cl2 gas. So these aren't ions anymore, they are in their standard state. The other thing I should note is all of these enthalpy changes we can assume we're dealing with in their standard enthalpy change. The bond dissociation enthalpy then is next. And since we're now talking about the breaking of bonds, this is always a positive value, and it is the enthalpy change when all the bonds of the same type in 1 mole of a gaseous molecule are broken. For example, Cl2 going to 2 Cl molecules in a gaseous state. Importantly, we're talking about a whole Cl2 molecule, and we're talking about the breaking of all of the covalent atoms. Covalent bonds between the 2 chlorine atoms. This is important, certainly when we go and compare it to the atomization of element, which we're about to do. So once again, we're talking about in the atomization of element, we're talking about bond breaking of a sort. So this is a positive value. But rather than in the example before where we were forming 2 chlorine atoms, we're now talking about just removing 1 chlorine atom. So the enthalpy change when 1 mole of a gaseous atom is formed from an element in its standard state. So this time we are half Cl2 gaseous molecules, going to 1 mole of chlorine atoms. So half a mole of chlorine molecules, Cl2, going to make 1 mole of chlorine atoms. What this does mean, of course, is that these two values are closely linked. For the instance of chlorine, the bond dissociation and the atomization, well, the bond dissociation, if I want to get to the atomization of an element, I divide by 2, and the bond dissociation as a value is twice that of the atomization of the element. And that's important because in exam questions you may require the atomization of an element such as chlorine, but you're given bond dissociation energy and you need to divide it by 2. Or vice versa, you may need the bond dissociation energy and you've got to multiply the atomization of chlorine element by 2 in order to get the bond dissociation. So you've got to be aware there of those two distinctions. So the atomization of a compound here, again, is always a positive value since we are breaking bonds. But this time we're talking about the enthalpy change when 1 mole of a compound in its standard state is converted into gaseous atoms. So rather than doing it stepwise, we're doing it as one whole reaction. We tend to look at atomization of elements rather than as whole compounds. The first ionization energy then we met before in the year 12 course when we were looking at mass spectroscopy, and the atomization energy is the enthalpy change when 1 mole of gaseous 1+ ions is formed from 1 mole of gaseous atoms. In this example we've got magnesium, gaseous atoms, and we are making gaseous 1+ ions plus 1 mole of electrons after the first ionization energy. Notice that this is a positive endothermic reaction because the electrons are attracted to the nucleus, and therefore we have to overcome this attraction in order to remove the electrons from the atom to make the positive ions. So the second ionization enthalpy is the next one we need to look at, and this is the enthalpy change when 1 mole of a gaseous 2+ ions is formed from 1 mole of gaseous 1+ ions. Again, this is positive, but notice, as with all of these things, and you should have seen this in your year 1 course, that the first ionization energy is going to be less than the second, and that's because the second ionization energy, you are removing an electron from a positive ion, and therefore that requires more energy to extract that electron. So the first electron affinity then, this is a new one in this thermodynamics section. This is the enthalpy change when 1 mole of gaseous 1- ions is made from 1 mole of gaseous atoms. Now this enthalpy change is always negative, and that is because there is an attractive force or an attraction between the electron and the positive nucleus, and therefore this is allowing us to release energy when the electron attaches itself to the atom and forming a negative ion. The second electron affinity then is the enthalpy change when 1 mole of gaseous 2- ions is made from 1 mole of gaseous 1- ions, and the example is O- gas plus an electron going to make O2-. This is a positive endothermic reaction because there is a repulsion between the outer electron and the negative ion. So therefore it requires energy to put this electron in. So our final 2 enthalpies here we're not going to use today, but we'll just add them here as completion for future lectures. We have the enthalpy of hydration, which is the enthalpy change when 1 mole of aqueous ions is formed from gaseous ions, such as Na+ gas to Na+ Aq. And the enthalpy change of solution is the enthalpy change when 1 mole of an ionic substance dissolves in enough solvent to form an infinite dilute solution. As I said, we will be using these in future lessons, but not today. What you do have to be able to do is you have to be able to learn and recall all of these definitions. And what we're going to go ahead and do now is see how we can use these to construct something called the Born Haber Cycles and calculate lattice enthalpies. So what we're now going to do is look how we can create something called a Born Haber cycle following these steps that we saw before, going through from ionic compound up to elements in their standard state, to gaseous atoms, to metal ions, back to gaseous ions, and then work out this unknown lattice enthalpy by constructing a Born Haber cycle. So what we're going to go ahead and do is now we're going to construct this Born Haber cycle for sodium chloride to work out the unknown lattice enthalpy of either formation or dissociation. And this we can describe here with the Born Haber cycle, where we've got profile And essentially we've got enthalpy change, or H on the side here, which is essentially energy. And we're always going to start off with our solid ionic lattice at the bottom as I construct these cycles. So for this one, we've got sodium chloride solid. And we're interested here in the lattice dissociation. So I'm going to draw here Na plus gas and Cl minus gas, because these are our ions of which we are going to dissociate. And I'm going to draw this unknown here because I'm interested in the dissociation. Draw this as a line up here. So I'm interested in the enthalpy change of lattice dissociation, and I want to find out what that is. So I can do this by drawing the Born Haber cycle and going through the steps. The first thing to do is to work out the enthalpy of formation, which is something that is known, and that is going from Na solid, that is the element in their standard state, to a half Cl2 gas, and that has got a value which we know. I'm going to just update this in green now. That's the enthalpy of formation there, and that has got a value of minus 411 kilojoules per mole. So we now have our elements in the standard state, but I'm trying to get them into the gaseous atoms and then gaseous ions. So the next thing I've got to do here is I'm going to get my sodium, for no particular reason I chose sodium, into a gas, and I'm going to leave the half Cl2 alone. And this can then be described as the enthalpy of atomisation for sodium, and this is a value that is known here and is plus 107 kilojoules per mole. The next thing I want to do then is I want to be able to find out or get the gaseous chlorine atoms. At the moment I've got half a mole of chlorine molecules, and I need to get these to chlorine atoms. So this time again I've now got the atomization energy, this time of chlorine, and this, remember, we've seen before, is half the bond dissociation energy of chlorine, again, which is readily available from data books, which is plus 122 kilojoules per mole. And the next step then is to get, we've now got gaseous ions, we're interested in getting, we've got the gaseous atoms, and want to get across to the gaseous ions. So the next step is to get the sodium into gaseous ions. So we have a sodium gas plus 1 mole of electrons, that's the first ionization energy. And we've got the chlorine atoms again, which are still gaseous. And this is the first ionization energy here of sodium, and that's got a value of plus 496 kilojoules per mole. And the final step then, going down here, is for the first electron affinity of the chlorine, and that's got a value again of minus 349 kilojoules per mole. Notice again the electron affinity is a negative, it's an exothermic process because there's an attractive force between the electron and the positive nucleus. So the question now is, what is this enthalpy change of lattice dissociation? So I'm just going to label this one number 6. I'm going to give the other ones a number just to make it easier for my calculation. So I'm going to say this is enthalpy change 1, 2, 3, 4 and 5. And I can describe then, as a result of what I saw last year in my Hess law, that the energy is independent of route taken, and also If I go against an arrow, I take it away, and if I go with an arrow, I add it. So in other words, going from sodium chloride solid to sodium gaseous ions and chloride ions is the same as going from delta H6, but I can also go for all the way round. I'll do this as a dotted line to there, and that is the same as going against enthalpy change 1, so minus the enthalpy of formation, with the enthalpy of atomization, with the atomization, with the first electron affinity. I'm still going with, first ionization energy, and I'm also going with the electron affinity here, because I'm still following that arrow back down. And if I actually put some numbers in here, I then have equal to, my value for this is gone, this was minus 411. So it's equal to brackets minus 411, the enthalpy of formation, plus 107, and I'd encourage you to leave the brackets on just to make your calculations a bit easier, plus 122, plus 496, and plus minus 349. And if we put that into our calculator, we should end up with an enthalpy of lattice dissociation, which is equal to 787 kilojoules per mole, if we follow that through. Okay, so there's quite a lot of steps there, and we're going to have a look at a couple more Born Haber cycles now. So in this next one, we're going to look at the Born Haber cycle for aluminium oxide, and we're going to see if we can calculate the unknown value for the lattice enthalpy of, in this case, lattice formation, because we're going from the gaseous ions to the solid product. And I've built most of this Born Haber cycle for us in this example, but we're going to see if we can fill in what each of the different sections are on each of the enthalpy changes. But again, it still follows a very similar route. We start off once again with the aluminium oxide as the ionic solid. We've got the gaseous ions up to the top right, and then we go from the ionic solid, we form into the elements, then we form it into the gases, and then from the gases we form in individual steps to the ionized gas, and then to the second ionized gas as well. So let's just go through and see how we were doing with naming some of these steps. So the first step here is once again is the enthalpy of formation for aluminium oxide, and this has got a value here of minus 1669. The second step then, we now have aluminium solid and 3.5 O2 or 3/2 O2 or 1.5 oxygens. And here we're then looking at turning the aluminium solid into an aluminium gas. Now, this is the atomization of aluminium, but notice that we have 2 aluminiums, so we require to multiply this by 2 times the atomization of aluminium. So this has got a value here, the atomization is 314, so we're 2 times 314 for this step. The next step then, we've got the atomization of oxygen this time, so we've got 3/2 O2 or 1.5 oxygens, and this is the atomization of oxygen, and we've got 3 of them. So this time we've got a value of 3 times 248. Now we've got our gaseous elements, and we need to get them into the ions. So again, we go stepwise. So this first step is the first ionization energy for aluminium, and we've got 2 aluminium, so this is 2 times the first ionization energy, and this is a value of 2 times 577. The second ionization energy then goes from the 1+ gaseous ion to the 2+ gaseous ion, and again we've got 2 of them, so that's 2 times the second ionization energy, and you'll notice that the value for the second ionization energy is much greater than the first ionization energy. Sorry, I've added a 1 there by accident. That's 1820 kilojoules per mole, and that's because we're now removing an electron from a positive ion rather than a neutral atom. We then have the third ionization energy, which again is higher once more, and we've got 2 of them because we've got 2 aluminiums, or 2 moles of aluminium, so we're now 2 times 2, 740. We now notice we've got 2 electrons forming in each step. That's because we've got 2 aluminiums, or 2 moles of aluminium, each releasing a mole of electrons each. So we have 2 moles of electrons formed in each step. We have 6 oxygens at the top, and this should read, of course, 3 oxygens, as we form 3 oxygens, so that's a slight error there at the top. And this first step down now, we're now looking at the first electron affinity here, and the first electron affinity for the oxygen. Notice we've got 3 of them, so we're now at 3 times by minus 142. Remember, this is an exothermic reaction because we've got an attractive force between the electrons and the positive nucleus. And this step here, just put this in here, we've got the second electron affinity, this one being positive, an endothermic reaction, because we've got a negative electrons being put into a negative nucleus. And again, apologies, that should say 302. So that's a positive value because of the repulsive force, so it's 3 times 844. Now, if I'm wanting to know what the lattice formation energy is, this is going to be the same as if I go around, against, and go this way around my Hess cycle, or around my Born Haber cycle, much like a Hess cycle. So, my value for the lattice formation we can work out as follows. The enthalpy of formation, or lattice formation, apologies, is going to be equal to, here, well, it's going against my initial second electron affinity, so minus 3 times 844. It's going against, once again, the first electron affinity, so it's minus 3 times minus 142. We're going against the third electron, third ionization energy, so it's minus 2 times 2740. We're minus again 2 times 1820. We're minus 2 times 577. I'm just going to come up here. We're minus 3 times 248. We're minus 2 times 314. And the final step there, the enthalpy of formation, we're plus minus 1669 kilojoules per mole. So if I put all of those into my calculator, you're going to end up with a value of minus 15421 kilojoules per mole. We just have to be careful there when you're putting your calculations in that you don't accidentally add or subtract values when you should be doing vice versa. So the final thing to look at is how we use the lattice formation data that we get at the end here. So the final thing that we're going to look at now is the theoretical and experimental enthalpies and what they can tell us about the bonding nature of our ionic lattices. Now, our Born Haber cycles give us a way of experimentally identifying the enthalpies of a ionic lattice. So the Born Haber allows us to predict here our experimental enthalpies. But theoretical values, well, these can be done via computers, etc., to determine what we expect the enthalpies to be. And a theoretical experiment will assume the pure model of a lattice. That assumes all ions are spherical and their charges are distributed around them. In other words, they are point charges, and the ions are spherical, and they look much like this example that we've got on the left hand side. This is our computer model and how we're going to make our prediction. However, that's not always a chain. What happens, because we might have differences in electronegativity and so on and so forth, and therefore we may not really have pure spheres of charge, but we might have a smearing like we do here, where we observe covalent character and where we've got electron density occurring between the ions, and these are no longer pure spheres and therefore no longer purely ionic. Why this is helpful? Well, let's look at our two examples at the bottom here. Here we've got magnesium chloride, magnesium bromide and magnesium iodide. Here we've got some experimental values used from the Born Haber, or taken from the Born Haber cycle. So these are true and they're calculated experimentally. This is from the theory, and this is assuming a purely ionic model. So here's our theory, and we can see that there's quite a large difference between the two. And importantly, that if we look at the actual experimental values, that the experiment is quite a lot bigger than the theory, and therefore we can assume that it is not a pure or purely ionic model, and that there is some covalent character to the bonding, and that is identifiable because the bond is actually stronger than if we assume a purely ionic system. The covalent character making our lattice stronger than we expect. However, if we look at this system on the right here, we've got sodium chloride, sodium bromide and sodium iodide. Our experimental values, which as said we are true, compared to our theory values, which we've got here, which we're taking from some sort of computer model, they are approximately equal. So the experimental is approximately equal to our theory, and therefore we can assume that we've got a purely, or it supports a purely ionic model, whereby we've got spheres of ions with charge evenly distributed. Okay, and that's essentially a key finding that we can get from these experiments. Please don't forget to check out the cards that you can see if you click on the information, and also these end credits for liking the videos, subscribing to more, and checking out the practical videos. I look forward to seeing you soon. So you should now be able just to define the terms: enthalpy of formation, ionisation, enthalpy of atomization, bond enthalpy, electron affinity, lattice enthalpy and enthalpy of hydration, construct Born Haber cycles and calculate lattice enthalpies and other enthalpy changes, and also compare theoretical and experimental lattice enthalpies as evidence for ionic or covalent character. Thanks a lot for watching. Please do like and share my videos. I'll see you soon. Bye for now.